We got a lot of participation out there for the brain stretch this morning. Good to see. Let's go ahead and go over it. So, in a reaction where the substances are click the wrong button. All right, in a reaction, the substances are chemically changing, right? So, if they're staying the same, then that's not a chemical reaction. That is a physical change, because in such that, right, if water freezes and turns to ice, or if it gets hot and turns to steam, then it's still chemically water. It's just changing the form into a solid or a gas, right? But chemically changing, like something like baking a cake, which has many reactions going on in it to produce the desired product that we want, right? It's making something that we didn't have before, but using the ingredients that we have. All right. In an exothermic reaction, right, heat is exiting the reaction or being released. So that's why if we place our hand or we touch the container where the reaction is taking place, it's going to feel hot to the touch. Whereas the opposite, being endothermic, heat is entering the reaction, and that's why it would feel cold to the touch. All right. Great job on that, everyone. Just a couple disclaimers as always. Please don't share any personal information during class. Participation is required, and these sessions are still being recorded for learning purposes. All right, we are on Tuesday today. Only 20 days left in the semester. Let's keep going. So our lessons today, we are balancing chemical equations in Unit 4. So we're going to learn all about how much of the stuff we're using. Specifically, we will define reactants, products, and coefficients in a chemical equation, and then balance that chemical equation as well. So with our notes and attendance, we have fresh links at the bottom of the chat. Let's go ahead, raise our hands for the notes. All right, let's try to do this quickly because we do have plenty to cover in today's lesson. Let's get started here. And when my timer goes off, I'll start calling on names.
Okay, can you hear me now?
Okay, there you go.
Perfect. Okay. All right, everyone. So this is a quick reminder that I am going on maternity leave in less than a week. Less than 2 weeks. So a week from yesterday, Monday, May 24th, I will be going on maternity leave, and I will not be returning for the remainder of trimester 3. So just as a heads up for that. So as a result, I am going to have office hours every single day for the next 2 weeks. I know it is bittersweet. I'm gonna miss y'all. So for the next 2 weeks, yes, I will have office hours every day at 2 p.m. to help out specifically with projects. Really, really recommend make sure you have your projects done before I leave, just because I don't really know what's going on with the sub situation. So I want to make sure that you guys are all kind of squared away and have everything that you need before I leave. All right, so remember that's our food project, that's our element project, and that is our friendship project, the most recent one. We haven't yet finished grading those, but those will get graded. Jen, I don't actually know. It's going to be a surprise. We didn't find out for our first kid, and we're not finding out for this one either. Yeah, so it'll be a surprise. Um, Along with this idea, we're going to go ahead and replace the Unit 4 project with the Unit 4 exam just to make it a little bit easier for grading for any subs that come in, any substitute teachers that might come in. Your final exam is still a final exam, so that has not changed. Again, you will end up just having 3 projects though for this trimester, so make sure those are all squared away before I leave. All right, let's go ahead and talk about chemical equations.
So chemical equations are very, very similar in purpose and kind of definition to a chemical reaction. It's just a different way of looking at it. So chemical equations are only describing what happens in a chemical reaction. So we have mainly 2 parts. We have the reactants and the products. The way I love to remember these names is that the reactants are kind of like our ingredients. They are what is reacting in the reaction. So that's where they get their name. The products is what we result with, or it's the ending product, as we would say, towards the end of the reaction once it's done and it's complete, right? So for product, that's what's being produced. Reactants are what's reacting. All right. In the chat, just really quick, let's do some observations of what do we see in the reaction to the right. All right. We can tell you that a copper is being dropped into a beaker of nitric acid. All right. What observations can we make that a reaction is occurring? All right. What visual signs? And the more specific, the better. You're saying the color changed. How did the color change? From what color to what color? To blue. Well, there's like a gold liquid, which is the nitric acid, and it does turn blue, but there's also like an orange vapor, almost like a very dark brown orange vapor coming out of it. Yeah, or smoke. It looks like smoke. One. What do we see the liquid in the beaker doing? Yeah, the vapor is darker. Good observation. So it's not boiling in a sense that we're boiling water, Tara, but probably I would guess that this reaction could be exothermic. So maybe whatever heat is being generated by the reaction, that could be causing the acid to increase in temperature and boil, but it's a different temperature than boiling water because it's not pure water. It is an acid. So yeah, it looks steamy. Observations, guys. Very good. So for number 2, we're going to write the word equations in our notes for number 2. And if anyone's curious, we do have kind of like the main observations we wanted to see, which was the color change, nitric acid turning blue, and bubbling orange vapor, which is the gas being formed, right? Those are the main 2 things we can tell that a reaction is occurring. But writing the word equations for number 2 in our notes.
All right, everyone, so let's go ahead and talk a little bit about chemical reactions and how we can represent them in equation form. So let's talk about water. So water is made from hydrogen and oxygen, H2 and O2. These are what are called diatomic molecules. So diatomic, take a look at the prefix di and tell me in the chat, what do you think the prefix di means? All right, tell me in the chat, what number do you think the prefix di means? Diatomic. What number do you think di means? Yeah, it actually means 2, right? You should be able to figure out like H2O2, right? So they're diatomic because they're 2 atom molecules. This is also why like carbon dioxide has 2 oxygens in it. All right, CO2 has 2 oxygens in it. All right, so diatomic molecules, these react to form H2O. So we have our reactants on the left, H2 and O2, reacting as shown by the arrow to form H2O, the product. The question though today though is we understand that we have reactions, but we need to figure out, is the reaction balanced? And this takes us back to unit 1 when we talked about conservation of energy and mass. Or matter, right? And this is the idea that you need to have the same number of atoms on the left and the right, because if atoms are just disappearing from the universe, that breaks this idea of conservation of matter. So let's go ahead and draw this out. Tell me in the chat, how many H's, how many hydrogen atoms are in H2? How many hydrogen atoms are in H2? Look at the subscript. Thank you. I see Tara, I see Rosa, I see Sophia, Alexis. Yeah, we have 2 hydrogens in H2. How many oxygens do we have in O2? How many oxygens in O2? Look at its subscript. Yeah, also 2. Awesome. How many hydrogens do we have then in our product in water? How many hydrogens do we have in our product, our water? Yeah, we actually also have 2 hydrogens in there. And how many O's do we have in our water? Again, it has a blank subscript. Blanks don't mean 0, they mean what? Blanks don't mean 0, they mean, yeah, 1 oxygen, right? So we've got 2 hydrogens on the left, 2 oxygens on the left, 2 hydrogens on the right, and 1 oxygen on the right. Is this balanced? Taking a look at the individual atoms of hydrogen and oxygen on the left and right, is this balanced? Yes or no? Excellent. I see Tara with an answer and a reason. Correct. No, this is not balanced. We're missing an oxygen over here on the right, so we're going to need to do something to fix this equation because otherwise it breaks the laws of physics. Okay? Literally. This is number 3. Please fill in the blank with the word diatomic, and then we're going to talk about how we're going to fix that. So 20 seconds, fill in the blank with the word diatomic. Okay, so the way in which we can actually balance these coefficients, all right, is going to be through, or sorry, balance these equations is going to be through something called coefficients. So coefficients are going to be big numbers that we're going to put in front of our molecules to show us how many of our big molecules overall do we need. So far we've been talking about subscripts, those tiny numbers that go at the bottom of our molecules to tell us how many of each atom we need. We just did that on the last slide, but this time we're going to start using big numbers. Again, our goal is to maintain conservation of matter, so the individual atoms on the left should be balanced with the individual atoms on the right side. Remember that any blank number just means 1. So if it doesn't have a coefficient, that just means 1. Doesn't mean 0. If it meant 0, we just wouldn't write it into the equation in the first place. So this is like, instead of saying like, hey, to make a cake you need butter, sugar, flour, and eggs, if I told you that, you would be like, that's not useful, Miss Larkin. I don't know how to make a cake because I don't know the amounts. So instead, now we have a balanced equation, right, where 1 cup of butter, which I left as a blank because blanks mean 1, 2 cups of sugar, 3 cups of flour, and 4 eggs will make 1 cake. All right, so we're going to see that in just a moment. This, though, is the answer to number 4. First blank is coefficients. Those big numbers are called coefficients. Second blank is that we need to balance the individual atoms. 40 seconds to raise your hands for number 4. Okay, so let's go ahead and actually begin to balance this equation. So I have what we already did together, all right, but now we need to go ahead and figure out how do we balance this. So taking a look here, which atom needs to be balanced, the hydrogens or the oxygens? Tell me in the chat. Let's review that. Which of these is currently not balanced on both the left and right side? Hydrogens or oxygens, H's or O's? H or O, which one do we need to balance? Yeah, we need to balance the oxygens, right? We've got 2 on the left, 1 on the right. That doesn't look right. All right, so which side needs more, the left side or the right side? Which side needs more oxygen? Perfect. Yes, the right side here needs more oxygen. Now, here's the deal. You can't just add random oxygens to the right-hand side to the product side because your product doesn't include random oxygens. You can only add more of what you have. So what is the only molecule that I have over here on the right? What is the only molecule that I can add more of on the right? It's in a box. I'm literally telling you the answer. What is the only molecule on the right-hand side that we can add more of? Thank you. I see Tara in the chat. Sophia Umeza, excellent to excellent. Yeah, we only have H2O on the right-hand side, so I can only add more H2Os on the product side. So let's add another H2O. So HHO. And now we need to recount the atoms. How many atoms of hydrogen, individual letters, H's, do you now see on the right side? Count up the individual H's. Yeah, we see 1, 2, 3, 4, 4 H's. And how many oxygens on the right-hand side? How many O's, individual O's? Yeah, you should see 1, 2. So 2 O's on the right-hand side now. Perfect. So oxygens are now balanced. Is our hydrogen balanced? Yes or no? Is our hydrogen still balanced? No, so we now need to go back and fix the hydrogen. So which side now needs more hydrogen? The left side with 2 or the right side with 4? Which side now needs more? Yeah, the left side needs more hydrogen, all right? And how can I add more hydrogen? Should I add another H2 or another O2? Again, I can't just add random hydrogens. I can only add molecules that I already have. So which molecule has the hydrogen I need? Yeah, we're going to add another H2. That's the only one that has the hydrogen that I need. So right here, we've got another HH. And now, how many hydrogens do we have on the left? Count up the individual H's. Individual H's. Thank you, Camila. Thank you, Rosa. Thank you, Tara. Yeah, we got 1, 2, 3, 4 individual H's here. Perfect. So now, is this balanced? Yes or no? Is this now balanced? Yes or no? Yes, absolutely. This is now balanced. Now, the last thing we need to do is figure out the coefficients, those big numbers that go in front of our molecules in our equation. Now, remember, this is important. Big circles or molecules equal big numbers, okay, are big coefficients. Okay, so tell me in the chat, how many big circles of H2 do you see here? For example, this right here is just one big circle of H2. How many big circles of H2 do you see? Thank you, Tara. Thank you, Rosa. I see Sophia. I know, Shane. Just practice with us, and then as you go, it'll begin to make more sense. Yep. So big circles, yeah, there are 2 big circles of H2. So that's going to become my big number in front of H2. Okay, smiley faces emojis if that's beginning to make sense. So the big number comes from the big circles. Okay, so after we've balanced the individual atoms, now we're just looking at the big circles. Cool. How many big circles of O2 do you see? How many big green circles of O2 do you see right here? Yeah, there's only one. All right, so I could put a 1 in front of here, or I can actually just leave it blank because blanks mean 1, right? So I could just leave it blank, means 1 for that one right here, okay? So 1, O2, all right? And how many big circles of H2O? Big orange / red circles of H2O do you see here? I used multiple colors. Yeah, so 1 on top. And then here's our second big circle of H2O of water on the bottom. So my big coefficient now tells me I need 2 H2Os here. Okay, this is literally the same exact thing that you're going to do on the very next slide. All right, we're just going to confirm that you understand what the diagram is showing you. So again, big circles tell us big molecules, tell us the big coefficients. Here we go.
Hydrogen and oxygen come together to make water. But all we're worried about, again, is the big circles that make the big coefficients. So go ahead, our whiteboard tool should be on. Place a box around the correct option that you think is the correct one based off how many big circles we are seeing. I'm counting 1 and 2 right there, and go ahead and just confirm that yes, this is the correct answer. The 2 going in front of the H2 and in front of the H2O. Go ahead, mark this down for number 5 in your notes. All right, I believe it's option D is the correct one. And raise your hands when you're ready to move forward.
All right, let's try another practice one. Eventually, you will need to be able to do the coefficients on your own for the last question, so let's make sure that we are practicing together. All right, do your best to participate because that will help you to feel more confident. Okay, so in this case, we have methane, a gas, reacting with oxygen, O2, to form carbon dioxide, water, and heat in the form of fire. Anytime we create fire, just so you know, this is what we call a combustion reaction. Many things can combust, right, because many things can be lit on fire, but combustion reactions will still form carbon dioxide, water, and fire on the product side. Now, methane is a gas that you might find, for example, if you use a gas stove. So let's go ahead and first draw out our molecules. How many carbons are in methane, CH4? Tell me in the chat. It's got a blank subscript. Blanks don't mean 0, they mean what? Blanks don't mean 0. Correct, they mean 1 carbon. And how many hydrogens are in CH4? How many hydrogens are in CH4? Look at that subscript. Yes, there are 4 of them, so let's draw those in. Now, O2 we already did on the last slide, so that is 2 oxygens. All right, what about CO2? Here's another one. How many carbons are in CO2? Blank subscript means 1 carbon. Beautiful. And how many oxygens are in CO2? Take a look at its new subscript here. Perfect. Yep, there are 2 oxygens there. And H2O we already did. We know that H2O is made up of 2 hydrogens and 1 oxygen. So counting up on the left, right, we said there was 1 carbon, 4 hydrogens, 2 oxygens so far. On the right-hand side, we see 1 carbon, 2 hydrogens. This one's a little bit tricky, though. How many oxygens do you actually see in total on our product side? Count them up from both the CO2 and the H2O. There's oxygen atoms in both of these molecules. Yeah, so actually there are 3 in total, right? You can see 1, 2, 3 right here. So we should have 3 oxygens in total on the right-hand side. So first things first, what do I need to balance? Carbon, hydrogen, or oxygen? Which one should I balance first? Good, I see Tara in the chat. I see Rosa, I see Matt. Yeah, let's balance our hydrogens. Our carbons look fine for now. So let's go ahead and take a look at our hydrogens. Which side needs more hydrogen? Left side we've got 4, right side we've got 2. Which side needs more? Which side needs more? Yeah, hand over a hydrogen. The right side. Now again, we can only add what we have. So should I add another CO2 or another H2O on the right-hand side? You can only add more molecules of what you have. So another CO2 or another H2O. Which one will give me more hydrogen? Yeah, we need more H2Os, right? Or we need more hydrogen, so I'm going to add H2O because that has hydrogen in it. All right, so let's recount then. So taking a look here, now how many hydrogens do I have on the right-hand side? Recount the individual atoms. Again, our goal is to balance the individual atoms, and then eventually we'll be able to find the coefficients. Yeah, we should be able to see 4 hydrogens on the right-hand side, right? So 1, 2, 3, 4. And don't forget, we did actually add an oxygen here. So how many oxygens do we now have on the right side? Remember, there's oxygens all over the place, so count them all up. Not quite 3, right? There's some from the CO2, some from this H2O, and some from this H2O. Yeah, we actually have 4 oxygens now on the right-hand side. Okay, smiley faces, emojis in the chat if that makes sense. Again, you have to count up all the oxygens on the right-hand side, all of them. Cool. So carbons are balanced, hydrogens are balanced. Let's fix our oxygens. Which side needs more oxygen? We've got 2 on the left, 2 on the right. Which side needs more? Yeah, actually the left side needs more oxygen, all right? And how can I add more oxygen? Should I add another CH4 or another O2 to my reactant side? Again, we can only add molecules of what we have, so which one will give me more oxygen? CH4 or O2? Yeah, let's go ahead and add another O2 here and see what happens. So we're going to go ahead and add another O2. That's the only molecule on the reactant side that has oxygen. And now, how many oxygens do we have on the left? Count up the individual ones. Yep, so you see 1, 2, 3, and 4. Awesome. So we now have 4 oxygens on the left. Is this now balanced? Yes or no? Tell me in the chat. Is this now balanced? Yes or no? All good, Tara. Yeah, this is absolutely balanced. So we have our atoms balanced. The last thing we need to do is now just fix the coefficients, the big numbers. So remember, big circles equals big coefficients. So tell me, how many big circles of CH4 do you see here? How many big circles of CH4 do you see? Big purple circles here. Yeah, you should just see 1, right? And so we could put up 1 in front of CH4, but again, 1 just means, 1 is the same thing as a blank. So I'm just going to actually leave that one blank. What about how many big circles of O2 do you see here? How many big circles of O2? Yeah, 1 big circle on top, 2 big circles on bottom, so that becomes my big coefficient. All right, now I've done the reactant side with you. On the next slide, you should be able to finish the product side. So here we go, let's practice this.
Let's look at how many big circles we have on each side. All right, the amount of big circles again is going to be equal to the number of the coefficient, right? That big number. All right, go ahead and box the correct answer that you think is the 1. Really quick, let's get some participation up there. All right, awesome. Oh man, let's pause that. And yeah, so the correct option is going to be B for number 6. B for number 6. Yeah, exactly. So go ahead and put that in your notes. I'll start a timer just really quick. All right, and be sure to raise your hand because we do have more to get through.
All right, everyone. So combustion reactions are super, super cool. So I do have an example of a combustion reaction up here. So this is my husband and I, like 8 years ago, doing a combustion reaction. So what happened here is we had methane that we bubbled up through soapy water. And if you wet your hands and then pick up the bubbles, since the fire goes up, it doesn't burn your hand because the water helps to insulate your hand. But this is really cool because once you pick up these bubbles of methane, you can then actually light that on fire and then look like a firebender. So this is a pretty cool science experiment here. I don't have a video of us doing this because it was a long time ago, but I have a video of the Mythbusters doing it. So let's go ahead and watch the Mythbusters doing this. Here we go.
They're going to weave some homemade magic of their own. First out of the blocks is Adam, and he's intending to set the World Wide Web alight with a towering inferno of soapy water.
We're trying something an old friend of mine gave me, which is that if you bubble methane up through soapy water, you'll end up with a column of bubbles. Because the methane's lighter than air, it helps lift the column and keep it stable. And then when that column gets a certain height, however high you want it, you can light it, and the whole thing goes whoom in flame.
And with a garden sprinkler on the end of a methane hose in a bucket of foamy water, it's not long before he has his very own bust of bubble.
I have been a bubble sculptor for about 20 years. The bubbles are a very fine way to sculpt the real world.
Their first attempt is a little lopsided, but Adam is poised to feed the fire of his pyromania.
That is so cool. It's water and it's burning. And now it's gone.
Second time around, and for Jamie and Adam, it's onwards and upwards. The bubbles are sticking together nicely, and the lighter-than-air methane is pulling the flammable column skywards.
At first, it's like, okay, it looks like it's working, but then it starts to get out into the area that defies physics.
Not only is it getting more fascinating, but it's increasing in funniness every minute. Okay, you ready? I just don't want to lose it. Wow! that was like a movie. That was like the beast dying at the end of the movie.
Well, I don't see anything on fire up there.
That was really cool. I have to say, for my money, that rivals the Canyon Soda. However, the Canyon Soda, that's safe enough for any 4-year-old to do. I mean, at least they're safe from everything except getting yelled at by their parents. This one, it's not safe pretty much for any of our viewers. We've done it. Now you don't have to.
All right, let me know your thoughts on that if you thought that was awesome, because I definitely get a kick out of it every single time I see it. And I've seen it a million times now, but it's amazing. Yeah, definitely don't do this at home. Just a reminder, don't do that at home, okay? Cool. I know, it is impressive, right? All right, let's go ahead and do our last one together here. So we have iron reacting with oxygen to form iron oxide. Iron oxide is also known as rust. Okay, so you can see rust down here. I am going to go ahead and show you, right, we've already got our equation kind of filled out here. You can see 1 iron here, right? We can see 2 oxygens in our O2. And over here on the right, you can see 2 irons and 3 oxygens in our iron oxide. All right, so let's go ahead and take a look at that. So let's go ahead and actually work on balancing this one together. And then again, the last question, you will have to find those coefficients on your own. So taking a look here, let's balance our irons first. Which side needs more iron, the left side or the right side? Which side needs more iron? Beautiful, yeah, the left side definitely needs more iron. So let's go ahead and add another iron over here. I'm not going to add an oxygen because that doesn't have the iron that I need. So we're going to add some iron here. And now we have how many irons on the left? How many irons do we now have on the left? Yeah, perfect. Now we have 2. So the irons look balanced for now. Let's go ahead and talk about the oxygen. Which side needs more oxygen? Which side needs more atoms of oxygen? Yeah, we need more oxygens on the left side. So how can I get more oxygen? So should I add another iron or another O2? Which of my 2 molecules, because I can only add molecules of what I have, will give me more oxygen? Yeah, O2. O2 is the only one that has oxygen in it. So let's add some more O2s here. So now how many oxygens do I have on the left? Individual oxygens, individual atoms. Count up the individual letters. Thank you, Tara. Thank you, Rosa. Let's get some more answers in the chat. Perfect. Yes. Yeah, we have 4 on the left. Now, is this balanced? Yes or no? No, we have a problem. We threw off our balance of oxygen. So now, which side needs more oxygen? The left side or the right side? Now, which side needs more? The right side actually needs more. So again, I can only add more of what I have. So I'm going to go ahead and add another rust here, iron oxide. And now recounting, how many irons do we now have on the right-hand side? Count up the individual Fe's. Individual Fe's. Sorry, let's start off with iron. Yeah, there you go, Rosa. All good. You were ready with an answer before I asked. Yeah, we have 4 of the irons. And how many oxygens do we now have on the right? Count up the individual letter O's on the right. How many oxygen atoms? Yeah, we have 6. Okay, now we still have a problem. This is not balanced. So take a look here. We've got 2 irons on the left, 4 on the right. How many more do we actually need on the left? How many more do we need on the left? Tell me in the chat. Yeah, so let me go ahead. We're just going to go ahead and kind of do both of them. So we do need 2 more irons on the left. So here's an FE. Here's another FE. So that one looks good now. Now we've got 4 on the left. And I still need more oxygen. Which side needs more oxygen? The left side or the right side? Left side or the right side? Yeah, the left side needs more oxygen. And how can I add more oxygen? Should I add another Fe or another O2? I can only add molecules of what I have. Yep. Let's go ahead and add another O2. That's the only thing that has the oxygen I need. And finally, how many O's are now on the left-hand side? How many O's are now on the left-hand side? Yeah, now there are 6. So is this balanced, yes or no? Yes, this is perfectly balanced. So all we need to do is figure out those coefficients, the big numbers in front. Don't put answers in the chat, but remember, big circles are going to give us those big coefficient numbers that we need. That's going to go ahead and be your last application. Here we go.
Need it. But yeah, so just multiple choice like we've done before, counting out the big circles to get those big coefficients. Raise your hand for number 7 once you have completed it. So great job today, guys. We learned all about how reactions work with reactants products in the chemical equation, and we learned how to balance and use coefficients. So go ahead, tell us how you feel about today's lesson using your color pointers. Again, keep in mind, I don't think we'll need it for this one, but keep in mind that there is still optional tutoring available all this week. Anyone want to share it? There we go. All right, so if you haven't turned in your notes already, go ahead and do so. Leave, log out, and have a great day. We'll see you guys tomorrow.